Thank you for tuning into Dyno Insights. In this episode, Mike and Chris will be discussing AC dynamometers.
Let's dig in. What do we got on topic for today?
I think today we'll talk about AC dynos.
Good topic.
So, as we start off, tell me a bit about what you know about ACs and why is it called an AC dyno?
Yeah, so I've been using AC dynamometers probably for the past 30 years, but they have evolved. So AC dynos were originally DC dynos. They were direct current dynos, and they had a lot of complexity with the maintenance on it, but they've evolved.
So just to interject,
Yeah.
you talk about AC and DC, so is this just really an electric motor running backwards? In principle, that we're using it?
Yeah, in theory. I think it is an electric motor, and it's how it's utilized. So an electric motor typically is just something that spins, right? You put power to it, and it spins. It uses power to spin. But with a dynamometer situation, you're spinning, but you're also absorbing power from whatever's connected to it. That's the principle of a difference between an electric motor and an electric motor used in a dynamometer. As a dynamometer, you have to absorb the power.
So it's effectively a generator that's resisting the prime mover, the test unit, and using the generating to slow the test unit down.
Exactly.
But with more sophisticated control?
Exactly. So when you look at, if you look at any electric motor, you've got a cable going into it and you plug it into a power source. With a dynamometer and an AC application dynamometer, you've got two devices you use. One is the drive unit, which powers it, but it's not just power. It has sophisticated controls built into it, and software algorithms that go into it. That's one part of an AC. The other part of it is you have to absorb the power, so you either have to put it back to the grid, the electrical grid in your public services, or you have to burn the power or absorb the power through a large resistor.
Or store it in a battery, I presume.
Or store it in a battery.
Good various sources you can put the electricity. You can move the electricity away from the dyno by a source. You can store it or put it back in the grid, as you say.
Exactly.
So these are sometimes referred to as electric motor dynos because of that background.
Mm-hmm.
Because of okay.
Yeah.
And where do you see these used on the most part?
So I think from all the dynamometers that we've spoke about, the ACs have the widest range of applications just because of its capabilities, right? So you've got 3 dynamometers, 2 which absorb only, and 1 that does both, which is the AC motor application. So you see them used in industries ranging from significantly small motors, such as a motor for a hair dryer. They actually dyno test those motors, those small little motors, all the way up through combustion diesel applications, high horsepower, but it does have limitations too. And I guess that's what, when we have our discussions, that's what we're driving towards, talking about its advantages and disadvantages.
Right. So the advantages seem to be flexibility from what you just described.
Absolutely.
Running a whole series of different tests from emissions to fuel economy to performance development. It seems pretty wide-ranging.
Yep. And again, like all dynamometers, they have their strengths and weaknesses. So when you look at its capabilities, it's the dynamic performance that really shines. It's the ability to switch between absorbing and motoring, running a specific test cycle for what you're testing. So while it does have the dynamic performance, it also has limitations. And some of the limitations that we can talk more in detail about is the ability to only go so fast at a certain power. So the higher power range that you have, the slower the capability is reduced from an RPM perspective. You can't spin as fast at higher horsepower. There's not electric motors of that size. So it leads to the questions of typically what industries do you see it in, which is you'll see it heavily used in automotive. It is in the diesel side, some of the off-highway stuff, because when I say that, they have to run government emissions based tests, and those tests specifically require a motoring dynamometer to utilize.
And this is quite a high response unit, so it can do the sort of on road testing and be responsive enough to replicate a road condition,
Yeah,
that sort of thing.
I think the coolest part of it all that people sometimes may not realize is that with a motor, you've got 100% torque at 0 RPM.
So it can put the load on straight away without
That's right.
any delay.
There basically is no torque curve from that extent from 0 RPM. It's almost a straight line.
But runs out as the speed gets to a certain point. It can only provide that torque resistance up to a point.
Correct.
Okay.
Correct. So from a standpoint of torque, response time, where you see it used, and you were starting to go down that path, Chris, standard emissions testing for the automotive engine or diesel engine, you'll see ACs heavily used in that because it's really the only dynamometer that can be utilized. You'll see it used in dynamic applications where, Chris, with your racing experience, simulating a Formula One race car is another application because it's used. Multiple dynamometers can be used in applications like that.
Running sort of overrun and running deceleration characteristics and things like that. It means you can motor and absorb. You'd switch between the two very quickly.
Right.
But Mike, what you're sort of saying is that the AC dyno does everything, so there must be a downside as well.
There is, and like I said, I touched on it a little bit. The downsides of AC dynamometers are, although their prices come down, they're still an expensive option. So the only time that you'd want to move over to an AC dynamometer is if you couldn't run a test and you were required to run a test that requires it. That's one reason. But that's one of the downsides. The other downside is there's quite a bit of electrical infrastructure associated with it. And typically normal facilities that you move into don't have the high power requirements that are necessary to meet the AC. So you have to bring in additional power. You may have to set some transformers up to bring in this additional power to be able to run multiple AC dynamometers. You may get away with one if it's small enough, but typically the electrical infrastructure is too small.
I presume there's still a cooling requirement, given that we're dissipating quite a bit of energy here.
Yeah, that's another important factor. So it depends on the city regulations or township regulations, wherever you're trying to install this AC application, whether you burn it or you store it in a battery, or you try to put it back to the electrical grid for the electrical company. And typically that's sometimes it is dictated actually by the township or city of whether you can do that or not first and what's required. And that can become quite expensive. And it becomes a limiting factor sometimes because if you hook up to the grid, they have the ability to shut you down without notification. So you could be running, they turn the power off. You can't regenerate power.
So if there's some infrastructure requirements, but what about the sort of the surroundings? Do you see these as noisy machines compared to, for example, water breaks or AGs?
Yeah, when we talk about noise, I assume you're referring to not audible noise, but more electrical noise interference?
Really a combination of both. You've still got a big rotor spinning in the machine.
Yeah, so I think from a physical sound perspective, I don't think is as a detriment as the noise perspective would need to be considered.
Okay.
Because the toughest thing in the test cell is when you get electrical noise or interference or signals that are dropping in or out or not reading correctly, it can be extremely difficult to identify and then just as difficult to eliminate.
Oh, that's interesting. So we've talked about quite a broad range of applications there. What would you say is the sort of one of the more unique applications of an AC?
I think what we touched on when we started going down the path of from the race industry perspective, because if you think about it, when you're watching Formula One or NASCAR, you're seeing the vehicles go down a set course. So as the vehicle's driving around the track, the inner wheel is spinning at a different rate than the outer wheels, and there's different forces being placed upon each wheel. And with an AC dynamometer, where I've seen powertrains set up where there's a AC dynamometer on each wheel, and there's actually an AC motor that's simulating the engine in the vehicle. So you have it all contained in a test cell without actually having the vehicle there. So you can simulate all the dynamic loads that the race car would see going into a curve, coming out of a curve, accelerating in, deceleration. All those things can be input into the control system for an AC dynamometer to simulate what the driver actually sees on the track with the vehicle that he's racing.
That's putting quite a bit of complexity into both the control and I suppose the dynamics of the AC driveline to be able to respond that quickly.
Yeah, and I think this is where it's bridging the gap in regards to software, right? So with eddy current dynamometers and water brake dynamometers, the software isn't as complex or dynamic as an AC motor because of what goes into it, what you're asking it to do. So there's a lot of work on the algorithm side of it. There's a lot of work on the overall software that goes into having that type of control.
Okay. Now, we've talked previously about the water brakes. We talked about the extremes of very high torque and low speed, or vice versa, very high speed, high power applications. Do you see the ACs getting into those areas as well?
I do. I think it's the natural transition for AC motor applications.
But at present, we have turboshaft engines spinning at up to 30,000 RPM.
Mm-hmm.
That sounds, from my knowledge so far, quite fast for an AC motor.
It is. You're absolutely correct. The speed versus power ratio is not the forte in the aerospace industry of an AC motor at this given point in time. It's not the application that fits an AC dynamometer application. I will say, though, based upon the industry and all of the companies, the larger companies developing electric motor powertrains, including aerospace, that the need for a matching AC dynamometer to test that is going to be required.
So that envelope is sort of stretching both in speed and power from the ACs.
Yeah. High speed, high power, low speed, high power, or high torque is the weaker areas of the AC dynamometer.
So,
but I do see them trending in that direction just based upon the technology from the powertrains in the various industries that it's driving the need for that.
And you said earlier that these are relatively expensive at the moment for a given sort of performance level. So in the future, do you see that changing as well? I mean, as well as stretching the capability, do you think the more standard machines will reduce in cost?
Yeah, I think they'll continue to go down in price. You know, if starting off, and use for an example, back in the day, when I say back in the day, say go back 20 years. So to buy a AC motor with a drive in the 250 horsepower category was probably $500,000. And today, depending upon the features, the options, you can get a 250 horsepower AC dynamometer combination drive system for half that.
That's quite a big change. So you expect that trend will continue?
I do, because there's more companies getting involved with it. There's a ton of motor manufacturers. There's a ton of drive manufacturers, and the more people that get into it, it's going to be more competitive. So it's going to continue to drive the prices down.
Okay, so it seems like in terms of the future, it's a good option in terms of flexibility, capacity to stretch to different applications.
Yeah, if I had a test facility that I was contemplating on building, obviously there's 1,000 questions that go with it, but I'd want to make it as flexible as possible. So if that is the case and the AC fit the performance range, then I would push to get that, because that would give me the most diverse capability for now and into the future.
That's an interesting way to summarize it. So it seems like you have a machine which has very good transient capabilities, good performance and speed range, but perhaps not reaching the specialized areas that some of the water brakes achieve today.
That's correct. You look at the technology and how long they've been around for the various dynamometers, and even with the water brake being around for over 100 years, it still operates in a market that others can't compete.
Right. Still can't get to some of those extremes.
Yep.
Oh, well, that's great. Well, thank you for that introduction to the AC dyno.
You're welcome.
And good discussion today. I think next time we need to talk about those 1,000 questions around the setting up of a test cell.
Yeah, maybe
look at some of the choices we make. Yeah. That sounds more reasonable. Perhaps.
Sounds good, Chris.
Thanks, Mike.
Thank you.
thank you for listening to Dyno Insights, presented by Frood. If there are any engine testing topics you would like us to discuss, we'd love to hear from you. Please email us at podcast@frooddyno.com.